All right, hello and welcome to the final week of instruction. You made it. We are here to review for the final. And the first thing that I want to direct you at is this link. It's from the optional reading at the very start of the semester. I gave you a link to this page, and you can go there now, and you should review all of the C++ language concepts, because you can understand all of this now. Okay? Got your main functions, got your function declarations, got your classes, references. I'm sure they talk about pointers eventually. They have inheritance and classes, destructors. There goes operators, templates. You now know how to do that. There comes exceptions, which is more of a 40 concept. Even smart pointers, if you want to brush up on those. So you can pretty much understand all of this now, and it's going to be a great way to review the C++ language concepts for the final. So please look into that. And then now let's get into the actual concepts that are more data structures-y and things like that. So let me review all this stuff now, including older things, stuff from before and on midterm 2, and then we'll get to newer stuff towards the end, maybe in the next lecture. So that's my plan, and all the stuff that we've talked about in this class can be a little bit dry, so let's pretend you are at an interview now. So you're interviewing at the famous company Amazon Buckle, and they have brought you into a room, and pretend that you are interviewing with them and trying to answer the questions that the interviewer poses to you. Okay, that'll make it a bit more fun, probably. So let's first talk about older stuff, so stuff from midterm 2 and before, and then we'll get into later stuff, okay? So let's first talk about just abstract data types, ADTs in general, and to get there we need to talk about data structures as well. So deep down, when you store things in your program, it's getting stored in memory, right? You have ones and zeros eventually, and a data structure is the concrete representation of data. You have like, okay, I'm going to put, here's my memory, it's a box. I'm going to put an int here, I'm going to put an int star here, and that int star is going to actually be pointing to that int, and then you have a bunch of other boxes with random like memory references to each other. So a data structure is just the values that you store in memory and the relationship between those values, okay? So this is all very concrete. This is your memory. That's what it means to be a data structure and to talk about data structures. Okay, so we learned about plenty of those, like linked lists. A linked list looks like, well, it's got a node, which the first thing is the data, and then the next thing is a pointer to the next node. Okay, and you know what it's like to have an empty list, how to mark the end of a list, things like that. Maybe you have a head pointer. So this is the arrangement of memory. That is a data structure, okay? Abstract data types, or ADTs, are more high level. They're like mathematical models of a certain type. And so instead of like lists, maybe we can talk about vectors, like C++'s vector implementation, like a vector of ints. It's more of a black box, right? It's any ADT is defined in terms of the operations that you can do on it. And we have no clue, like if this is our vector v, we have no clue if it's actually using an array. It should if it's normal, but it doesn't have to. We don't care about its undefined or its underlying representation. It's unspecified. As long as a vector, which is a black box, as long as it responds to our commands like a vector should, it fulfills all the requirements of being a vector, like, hey, push back, please. 42, and then it'll say, like, okay, yeah, cool. Sure. And then you can go and ask it, hey, what's at index 0, and then maybe it'll give you back 42. As long as it plays this game properly, it's a vector. It doesn't matter if it has an array inside of it. It doesn't matter. Maybe it stores its information in a list, and it's very slow when you're trying to access an index. That's not the first or the last. So that's the key difference between data structures and abstract data types. You can use data structures to implement an abstract data type. You can go from there to there. That's not a problem. But a data structure is the memory itself, the arrangement of memory, how you're storing things exactly. And then an abstract data type is, of course, more abstract. It's a black box. It is defined in terms of operations. Okay, hopefully that is all coming back to you or making it a bit more clear in your mind. Let's move on now to the heap. So it is a beautiful place where you can store dynamically allocated things. So the things that we've been talking about, or most of the things you learn in CSCI 40, for example, are, when you make a variable, it's a local variable, and it lives inside of a function on the stack, for example. So maybe you say, I don't know, here's your main function, and you say something like, this is the stack, you say something like int star I equals new int. And what this does, the new, is it makes dynamic memory in this place called the heap, which is separate from the stack. On the fly, it makes a shiny brand new int, and we could give it something. Maybe I could use its constructor if I wanted to. How about we do that? Constructor style initialization, even though an int is not a class. So that'll make this thing on the heap that holds 42, and then I is the local variable. It has a name. It lives on the stack in main, let's say. So I is here, and maybe the address is 100, so I will hold 100, and bam, it points to 42 like that. So the heap is a place where you can store dynamic memory that lives as long as you want. So if main were to go away, or maybe this wasn't main, it was like foo, it does nothing to this heap variable. It does something to the variable that holds that address, which you might have just lost it, but if you save it somewhere else, then it will live for as long as you ask it to. So new works with any type, including arrays. You say new t, and you get back a pointer to a t on the heap. Okay? You can also say new t of size 42, and that makes an array of 42 t's on the heap. And that t thing lives forever, or until you say delete. Okay, so I can then go and say delete I. Delete takes a pointer to something on the heap and goes and gets rid of it. Okay, and yeah, t itself can be anything. It can be a class, it can be like a vector, it can be a primitive type like an int, it can be an array of anything, like an array of some other type, u, things like that. So the heap is a beautiful place where you can make whatever you want and it lives for as long as you want. Okay, as long as you have a pointer to it, you're solid, and you don't want to lose any pointers to things on the heap because that's a memory leak. We don't like those. Okay. So with that, that's the heap. Let's move on now to stacks and queues. So, let's talk about, well, these are both ADTs, first of all. Remember that. So a stack and a queue, they're slightly different, but they have very similar operations. So they both have an operation called push, which adds something. Stacks have top, whereas queues have front. They both have pop, and they both have a way to check if they're empty, because they hold things. They're containers. All right, so let's talk about stacks. As I draw a queue accidentally. 1, 2. So stacks have a concept of the top of the stack, and when you push something, it becomes the new top. Okay? So if you were to push something, it would go up here. Push adds to top. So maybe you're going to push 4 or something. And then pop, for a stack, it removes from the top. Okay? Okay, that's a stack in a nutshell. And we'll get into these words in a second after I explain queues again. So a queue is more like a line of people waiting. Maybe I have 1, 2, 3. And that's the end of it. It has the concept of the front of the queue and like the end, the back, or the rear of the queue. And if you were to push something to the queue, like dotted 4, so push adds to the back. That's the one key. It's the real key difference between stacks and queues, the place where you push and the place where you pop. I guess technically you can think of the place where you're popping as the same place, because popping will remove the front, okay? So it kind of goes together. Where you can access, that place that you usually want to access, is the place that then gets popped. So you pop either the top or the front. You see that? And you have quick access to the top and the front. That's the idea. So those go together. And then we made some cool acronyms to talk about these, just to try and understand them better. Stacks are what are known as LIFO, which means last in, first out. The last thing you put in is the first thing that you get rid of when you pop. That's what it means to be a stack. It's kind of like the last person has the floor, has priority. Whereas queues, they're nice and orderly. They're people waiting in line. They are FIFO, which means first in, first out. So the first thing that you put into the queue is the first thing that you take out when you pop it. Okay, everybody's waiting nicely in line and nobody's cutting. All right, so my example problem for you is something that you can use a stack for. Example problem with stacks. Checking for whether or not some parentheses are balanced. So if you give like if you give me a string containing parentheses that look like this, maybe. Let me draw them out a little bit more. Maybe like that. Honestly, that's probably enough. If you give me a string that looks like this, we can use stacks to determine whether or not these parentheses were balanced, which is fun to think about. So let's talk about how you might implement that. So I encourage you to implement this. I don't have enough time to implement everything today. So the idea is you put, you push to the stack when you see a open brace, or open parenthesis. So here is our example. So you're going to read it from left to right, this string. You'll look at the first character, then the second character, then the third character. And when you look at these strings, you're going to notice it's either an open paren or a closed paren. If you see an open one, you push to your stack. And then whenever you see a closed paren, you pop the stack. And this will allow you to check whether or not these parentheses are balanced. Because if we walk through this, I'm going to push the open paren, push the open paren, pop, pop, push the open paren. This is really an empty stack at this point, but I'm just not going to get rid of things. Pop, and oh man, it's empty. So if the stack is empty, it was balanced. If once you're done going through everything, the stack is empty, then it was balanced. And this is a guarantee. Otherwise, either the stack wasn't empty or you tried to pop an empty stack. The stack wasn't empty at the end. Or you popped an empty stack. You got an exception. Then it wasn't balanced. So for example, like maybe there was an extra closed paren, which means you try to pop an empty stack, fail. Suppose there was an extra open paren, which means you would leave a stack. You'd leave this parenthesis waiting to be closed. It would be, I guess, this one. Or, no, it would be this one. That would be waiting to be closed, and so it leaves the stack at the very end non-empty. Okay, I hope you see that. So that's a fun little example of stacks, and now you know another thing that you can use them for. So push when you see an open paren, pop when you see a closed paren. That's a neat example of stacks. So hopefully that comes back to your mind. And remember how to implement stacks. Stacks and queues, usually implemented using linked lists. You have to have a very good reason if you're not going to use a linked list to implement these. All right, moving on. The next thing that I want to show you is just a fancy example of classes. So I want to teach you how to make your own iterators. We've been using ones that have been made for us, but let's make our own finally. So let's make an iterator that goes through a range of values. Like if I say I want to go through the range from 1 to 32. That's like I want to iterate from 1, I is 1, to all the way 3, 4, 5, all the way to 32. So I can make a class called range that keeps track of the start and end points, and then I can actually make my own iterator for ranges so that when I go through it using the range-based for loop, it actually works. It makes I first 1, then 2, then 3, then 4, all the way to 32. That's pretty cool, huh? So let me show you how to make that. And the idea for any iterator, like we had our iterator IT back in the day, all it does is store where you are in something. Usually it's like, okay, we're in some data structure like an array. It needs to store where you are. Okay, it's like, okay, I have a pointer somewhere in that iterator that's pointing to where I am. And when I say IT++, or we're going to need to use ++ IT because that's what this gets translated into, then it just magically advances the iterator. And like you can use it again when you star IT. It like gets this thing. It's all beautiful, but an iterator is just storing where you are. Iterators are classes that store where you are in something. Okay, that is the idea for that. And yeah, so ranges, all you need to store is like, where am I? Where am I and where am I going? All right, so maybe our IT can just keep track of, okay, my current index. Where am I? We can store like, okay, it starts at 1. Then IT++ makes that index now 2, or not an index, it's just a number. And dereferencing the iterator gets the value. Things like that. So all you need, if you want to make an iterator, is you need a .begin and a .end method. That gives you back iterators for your ranges. And then on the iterator itself, you need the ++ operator, the dereference operator, and actually the not equal to operator. And I'll talk about why. Okay, so that's enough talk. Let me show you what I've implemented. I've just gone and pre-implemented everything here. So, dun. Don't worry about the vector stuff just yet. Here's what we want to do. We want to make a range that goes from like 1 to 5, and we want to be able to iterate between 1 and 5. So I'm going to make a class called range iterator that gets returned when I say r.begin or r.end. I'm going to implement those begin and end methods. So now I have range iterators that I can be like, okay, yeah, a range between the beginning of R and don't go past the end of it, and advance it every time you loop, and star IT will print the 1, the 2, the 3, the 4, the 5, because we're ranging through those values. Isn't that fun? So if I show you the output of this program, oops. Yeah. Just look at the first thing. It's going to go and print from 1 to 5, which is beautiful. It's making IT store like where we are. So, and star IT gets the thing. So let's see what it means to be a range. It needs a starting point and an ending point. So here is what it means to be a range. It just stores the start and the end. I use underscores because I've also overridden the end. Like, we need this to be called exactly end for reasons. And so it just has a constructor that saves the start and the end point when we make a range between like 1 and 5. It saves those using the initializer list. And then also we have these begin and end methods that return iterators. So iterators on ranges, which the first beginning point will hold a iterator that starts at the starting index, or the starting number, and then end is supposed to always be something that you don't want to get to, so it's one past the real end. So the last number plus 1 is the idea there. Okay? So a range iterator now is just going to store where you are. Okay? That's all it needs to do. Current spot in the range, please store that in our range iterator. And so its constructor will just take that and store where it currently is. And now, to dereference it, the operator star, you just return where you are in the range to get out the 1, get out the 2. Plus plus just advances your current spot in the range. And then not equals to, with another range iterator, just needs to compare like, okay, I'm equal if my spot is equal, so I'm not equal if my spots are not equal. That's the idea there. And so with these, you can make this for loop, and it'll work. And it'll range between 1 and 5. IT will technically point between 1 and 5. And now the magic is you can use the range-based for loop with our range and our range iterators. This syntax gets translated from C++. It just does it for you. It gets translated into exactly this code. Okay, under the hood, it's probably using auto instead of range iterator, but nonetheless, it's getting translated into this exact code, and so it needs the begin and the end to work. It needs this plus plus operator. It needs the star operator, and with that, it can actually make this work. Okay, and so the second thing is exactly equivalent, and we got it for free just because we called everything the right names. Isn't that fun? And so then I want to show you how we can make our own custom vector iterators. Again, we just need to store where we are. Again, we can store like the index. Our iterator can store the current index where we are in the vector, maybe index 0. And then we also need like a pointer somehow, or maybe a reference to the vector itself. So we can, like, when we say star IT, we can actually go to v at that index. Okay, so all you need to do for a vector iterator is hold where you are in that vector. So here's my class, vector iterator. It stores your current index and also the vector itself, so we can have it and iterate through it, right? So when we make a vector iterator, we just give the vector in our current starting location. Again, the dereference of the iterator is like following the pointer that is not really a pointer. We're getting the thing at v's index where we currently are. Okay, just go there. We found it. That's what we want. And then operator plus plus advances our current index, and not equal to, again, just technically we should probably check if we're the same v, but this is good enough for our purposes. We'll check whether or not our current index is the same, or whether it's different, that is. And then we can't really like add methods to the vector class, so we'll just make functions. So vector begin, how do we get the begin of a vector? Give it back as a vector custom iterator. Well, just return a vector iterator with v, of course, starting at index 0. That's the beginning of the vector. If we were to dereference it, we get v at 0. And then the ending point of the vector again would be v again. Use v, but 1 past the end, so we don't want to hit the end, we want to go 1 past it, so we want to stop when we get here. The last valid index is v.size minus 1, so the first index that is invalid is v.size, right? Because maybe you have 5 things, you have indices 0 through 4, you don't want to touch index 5. Okay, so with that, we can now, we can't actually make this because it would require having like v.begin, which technically already exists, but we made our own. So we can say vector iterator it equals vector begin v. It's not equal to vector end v plus plus it. And then it just all works. So I encourage you to study this code and understand why it's like, okay, it's just saving, I'm at index 1. Let's get out, let's get the 1. Or actually, just so that the indices aren't the same as the numbers. I guess technically they're not. Just to, because it was 0, 1, and 2, wasn't it? It'll go to that thing, advance the iterator, go to the next index, advance the iterator, go to the next index, and once it gets past the end, we'll stop. Okay, hopefully that's making sense. Just a neat example. Okay, moving on now to complexity. So I know I'm going all over the place. There's a lot that I want to talk about, and there's a lot you asked me to talk about in your check-in survey. So I'm trying to hit everything. But please come to office hours if you have any burning questions about this stuff that I may be glossing over. So complexity is something that's very dear to our hearts in computer science, because we want to know how fast something's going to run, usually, or how much space it's going to use, or some other thing. So normally we use big O notation to keep track of how fast something grows. It's a mathematical concept. It just really means how fast a function grows. But at least in computer science, this is nice for us still, because we can associate functions with our algorithms that we write. Okay? So that's quite nice. And remember, when I say big O, we really mean big theta, because we want the tightest possible bound. It does no good telling me that, oh yes, n plus 17, oh yeah, that's O of n to the 5. That's useless. So always use the tightest bound. And when we're talking about things, when we're coming up with functions that represent our algorithms, we have different cases that we can consider. We have the worst case, the best case, the average case. All right? And remember all of those. Remember this website that has all those. Boop. Most of these are accurate. Okay. And then we have how we use big O. We say something like this: f of n equals O of g of n. And we say it in English like f. We pronounce it f is O. F is big O of g. F is O of g. And what this means mathematically, if you care, is that there are two constants. There is a c, and then there's an n naught, such that if you try any value of the function from n naught onward, the value of f of n is smaller than the value of c times g of n. Okay, so for some constant multiple of g, it always dominates f. And so we say that f grows no faster than g. And this is really nice for us because it allows us to simplify our fancy operations. We say okay, n squared plus 17n plus 42, well, that's just big O of n squared. It gets rid of the useless stuff because those smaller terms, those smaller order terms, go away when n gets big anyways. So we don't really care as much about them. And same with constants. If n squared and 17, or n cubed and 17n squared are completely different. So you might as well just drop those too. So you drop lower order terms, remember that. Drop lower order terms, and then also you drop any leading constants. Because eventually you can find a big enough constant to put on g of n anyway. So hopefully that makes sense, and the mathematical definition is helpful. So normally, we really like about what we really like about big O is that we can come up with functions that describe how fast something executes. We usually care about runtime complexity most of all in computer science. Not so much space complexity, because RAM is cheap. Time is money, right? Okay, so yeah, we really care about how long it takes to execute an algorithm on a given input. And so what we do is we always count the number of basic operations. Okay? So a basic operation, that's something that you'll understand more when you take CSCI 45 or CSCI 26. You can think of it as a very simple line of code. You're essentially counting the number of lines of code that don't do anything fancy, like loop or call functions that loop, or recurse, or things like that. So that's essentially what you're doing when you're calculating runtime complexity. And there's a bunch of different common ones that we've used and talked about all over the time, all over this class. And let's talk about a few of them. So a constant time thing, it's something that takes a countable number of lines, and it's always the same count. So for example, if we made a function called sum23, that's okay, yeah, just return, maybe the parameters were x and y, return x plus y. That is one basic operation to do the addition, one basic operation to return from a function, it's essentially, it is constant time, no matter what. Okay, so that's constant time thing to talk about. You can count the number of lines of code, and it never changes. Okay, so like the number of operations never changes. And then the next fastest thing is a logarithmic time algorithm, and binary search is a great example of that. And the reason it is logarithmic is because you have like an array, and you're always cutting off, like initially your entire search space, like the thing that you're looking for, it could be anywhere, so your search space is the whole array. But then once you start making comparisons against the middle of the array, you can start cutting off sides. Like, okay, it has to be in this part of the array now because the array is sorted. And then you'll cut off another side, like, oh, okay, it must be in this side. It must be in this side. And eventually you'll get down until either you have one element or 0 elements, and it takes log of n tries to get there. Log of n times on the order of log of n comparisons to like get to a size 1 or size 0 search space. So that's binary search. Remember how to do it and what it's good for. Okay, the next smallest thing is linear time. Just remember how to do that. Linear search is just, okay, we gotta look from left to right through this entire array, and we have no clue where the thing is because the array is not sorted. Okay, there's no guarantee about where it is, so we have to look for this value everywhere. So that's linear search. You have to try all n things because this array has n elements, right? N elements. And then we have some other things that we've talked about. Merge sort is a very fast sorting algorithm, and it's n log n time because it recursively sorts half the subarray, half the array each time. And eventually it's got log of n levels in its recursion tree. And then at each level of the recursion tree, it has to merge n things. And that multiplied together makes n log n. And then your n squared, n cubed, n to the blah, 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 it's always just a bunch of nested loops, usually. So you think of it like, okay, 4 is between I, for I is between 1 and n, and then inside of that you have another loop like for j is 2 to n over 2. Still though, this is like n over 2 minus 1 iterations. This is n iterations. You multiply them, you drop all the constants, it's still n squared. Yeah? That's the idea. So runtime complexity, just get a feel for how it all works. Remember your standard examples of all these things, and that will really come in handy on the final, I think. Space complexity is important still, and it's important to understand how to get come up with the function. Again, we're making a function, and we're not counting execution. We're not counting lines of code anymore. We're counting not basic operations, but like the number of bytes that are used by your program as it runs, as it executes this algorithm. So think of it as like how much stuff do you need to store based on the size of the input that you're given. So for example, if you need to make, I don't know, 3 ints for your program inside of your function, like this is your foo algorithm, that's its stack frame. If you need 3 ints, x, y, and z, then you have constant space. Because each int is 32 bits long, 4 bytes, so 4, 8, 12 bytes, and you have everything you need for your algorithm. It's countable, it never changes, it's constant. Okay, that's constant space. And recursion is something that can trip you up with calculating space complexity, because you need to include the stack in your calculation. Or the stack is going to have a bunch of functions that are the same, your algorithm, on it. And the stack's going to keep growing until you hit the base case, like for a factorial, for example. You call from main, like, all right, calculate 4 factorial, which will go and calculate 3 factorial first, which will calculate 2 factorial, which will calculate 1 factorial, which will calculate 0 factorial, and that's the base case. Now it can start popping off the stack. But it needed to store all of its information on the stack. This is O of n function calls, each using, for factorial, you just need to save the parameter. It was 4, 3, 2, 1, and 0. 4, 3, 2, 1, and 0. Each using constant space. So it would be an error to say, oh yes, each function just needs one variable, it's constant space to run this factorial algorithm. Well, in the best case, yes, but in the worst case, you multiply the space complexity of a single function call by the worst case number of function calls. So in this case, it's going to be O of n times 1, O of n space complexity. Okay? Hopefully that's making some sense. It's clear in your mind now. That's space complexity in a nutshell. Again, I have to give everything to you in a nutshell, sadly. Please come to office hours if you want information about any of these topics in more detail. I'd be happy to give that to you. Okay, I'm just trying to cover all the bases this time in this review lecture. All right, hashing and hash functions is something that a couple of you wanted me to talk about, so let's get into that. Just from a high level, hashing is all about, like, we want to look up things in a table. We only have so much space, like we have indices, I don't know, 0, 1, 0, 1, 2, all the way down to like 42. That's all we got. And we want to store stuff inside of them. We have keys we want to store. Maybe they have values as well. And hashing is the way to take a finite-sized array and store whatever you want inside of them. Okay? So the idea is, yeah, it's super easy to store keys from 0 to 42, but what if you have a number that's bigger than that, or negative, or you have some other type? And that's where hashing comes into play. You can take any type, and that can be the key for your lookup table. Okay? You just need to use a hash function, and a hash function is going to go and turn that type t into an index of your lookup table. Eventually, it's going to turn that type into a big number, into a large non-negative number. And then you can turn that into an index of your lookup table. Okay, so every hash function takes a type t and it turns it into an unsigned int, usually, which is a non-negative number that you can then mod by to get to a valid index. All right, so maybe you want to like put in your hash table hi mom, which is a string. So where in the world is it going to go is the question. And that's why you make a hash function. Maybe your hash function for strings is you just take each ASCII code for each character, like this is 40, this is 42, who knows, and you just sum them all together. And maybe the hash function that you give back, like your answer for hi mom's hash is, I don't know, 227. And then all you need to do is mod by your table size to get a valid index. Okay, so maybe it's like, okay, I'm going to put hi mom at index 1 now, for example. And so I'll put hi mom there. And there's a bunch of different ways now to hold stuff in your hash table. We've talked about a few. You got your chaining, you've got your use the hash table, open hashing, close hashing, right? So you can either use linked lists at each index to handle collisions when multiple things get mapped to the same index initially, or you can start looking at free indices in the hash table somewhere else. Like you can use linear probing, quadratic probing, double hashing. Remember all of these. And hash tables are really nice, and remember all your complexities. So we have a hash table. Hash tables, on average, are constant time lookup. And that's when your collisions, the average number of collisions for each key is constant. It has nothing to do with the size of the table n. At that point, the average lookup time, therefore, becomes constant, because you only have to check a constant number of indices in the worst, or in the average case. Okay? In the worst case, like everybody's mapping to the same thing, and then you have n in your average number of collisions calculation, at which point the lookup time gets horrible. But on average, usually, this is really nice and really fast. Okay, so that's hashing and hash functions. And now, just one after another. We're going to move on. Binary search trees now. So a number of you wanted me to talk about this. Do watch the midterm 2 review video as well, just to hear me talk about this twice. So the BST operations, the BST is a data structure, by the way. You can have it, BST is a data structure. You can make you can make maps out of them. C++ uses map, and then also set using BSTs, balanced BSTs. So you can hold keys and values, but the BST itself is okay, how's the memory arranged? We have parent pointers, we have lefts and rights. BST is a data structure. So you can do a bunch of things to your data structure. You can search for stuff, insert stuff, and remove stuff. Maybe you have key values. Okay, and I'll talk about this in detail, but all of these, for an unbalanced BST, which is the kind that we care about in this class, in a fancier algorithms class that you'll take eventually, you will start balancing your trees. But let's see here. Just remember that all of these have to do with the size of the tree. Okay? In the worst case, you need to get to the bottom of the tree to do everything. Like you're looking for the 1, you got to go down the height of the tree. You got to go insert over here. You got to go down the height of the tree to search to where to insert the thing. You got to remove down here in the last node of the tree. You got to find it first, but also you need to find its predecessor sometimes. Oop, if you're trying to remove that node, for example. Yeah, a lot of things going on. Remember your recursive operations. Please study those. Those are your traversals. I'll give you an example that we haven't looked at yet of just a recursive operation on a BST later. Just remember all that stuff. Okay, so let's talk about each of these in detail and understand why they're O of H. So remember your BSTs, everything here is smaller than the root. It's all from every node's point of view. The subtree is always smaller. Smaller than 5, greater than 5. And you can talk about each of these as well. This is smaller than 3, this is greater than 3, things like that. Okay, search now. So you always start your search at the root. This is what you store in your ADT or something. This is how you hold a BST. You hold the root pointer. You don't go holding pointers to any of the other nodes usually. So you're starting at the root and you're searching for something. You're looking for some value. So if what you're looking for is smaller, you're going to go left. If it's bigger, you go right. If it's equal, you found it. That's the algorithm. Okay? Do look at your book. Your book has all of this stuff implemented. It would be a great idea to study these algorithms and understand how to implement them. Okay? Just from scratch. So let's say we're looking for this 4. Okay, we want to find the 4. We don't know where it is. We start at the root. So we see the 5. Well, we know immediately that we better go left because the 4 is smaller. So then we get here. Okay, I see the 3. What am I going to do? Well, the 3 is smaller than what I'm looking for. So I know if the thing that I'm looking for exists in the tree, I better go right. So then I'm here and I finally find the 4. If, however, I was looking for 3.5 or something, I would go left once more and not find the thing. So in either of those cases, I have to, in the worst case, visit the height of the tree, because I have to visit, I have to go down to a leaf at the lowest level. Here's level 0, level 1, level 2. Okay, I have to go down here and get somewhere. Either I find the thing or I don't find the thing. I have to make, on the order of the height of the tree, comparisons, because I have to look at this node, compare its value, look at this node, compare its value, look at this node, compare its value. Okay, that's O of H in the worst case, and so that's really why you want your trees to be balanced, because H turns into logarithmic. H turns into log of n, which is super duper nice, because in the worst case you got a tree that looks like this. It's essentially a linked list, and then you have it's O of n, right? H equals n. Okay. Now for insert, you actually kind of know what to do. You essentially want to search for what you want to insert. So for example, let me try and insert 11. We have to find out that we need to go here. Like, okay, it's bigger than 5, bigger than 8, smaller than 13. So I need to put my 11 node right here. Okay, so you have to search for the key that you want to insert. And if you find it, you're good. You're done. But if you don't, then you insert it at the place where you would have found it. That's the idea. You have to do the search because you need to find out, like, okay, I got to put it to the left because I want to find it. If I were searching, I would find it to the left of here. And there's nothing there right now. So I'm going to put it there. Okay, that's where the 11 node needs to go. And yeah, it's super constant. Like once you know where to go, like this is the parent. It's super easy to like make the node, set its left and right pointers to null, set its parent pointer to the 13. That's all constant work, but it's O of H to search. That's the bottleneck, to search for where that node should be. So in total, it's O of H time to insert in a binary search tree. Okay, hopefully this is all coming together, and just seeing it again is making more sense. Okay, removal is the hard one, as evidenced by your lab, of course. So there are a few cases. 1, 2, and 3, I call them. The first case is the easiest. If you were going to get rid of a leaf, for example, oops, I have some stray green. If you're going to get rid of a leaf, let's say we're getting rid of 4, you can just like go to it and get rid of it. Just say, boop, it's gone. So again, once you have a pointer there, it's really fast to get rid of it. So you just make the parent forget about it. Like, okay, now this right child is null, and the 4 gets deleted. It's all constant work. Okay. If you find a node that has 1 child, that's also very easy to handle because remember that there's also parent pointers involved, as well as left and right pointers. Well, if we're getting rid of 8, for example, we can just delete it, but before we do, we set the 5 nodes right child, and then we set the parent pointer of 13 to not point to 8 anymore, but we point it to 5. Okay, so just swapping around some pointers. Again, it's constant. Okay? And also, additionally, you may have changed the root in cases 1 and 2. So maybe the tree looked like this. If you got rid of the root, maybe it had 1 child or no children, and then you make a new root. So just watch out for that special case of cases 1 and 2. You might potentially change the root. In case 3, you have 2 children. You're trying to get rid of maybe the 5 node, and it has 2 children. In which case, you need to now swap things. You're not actually going to remove this node. You're going to remove the predecessor node or the successor node, for example. Okay, you pick one. They'll both exist, so just pick your favorite and swap with that and delete that. Okay, and once you try and do that, you are guaranteed to be in one of those easier cases because, for example, like this is if we're going to swap with the predecessor, 5 is now down here, and it's super easy to get rid of 5. Yeah. So you're guaranteed to be in one of the easier 2 cases because the predecessor cannot have a right child because it may have a left child. It can't have a right child because that would have been the predecessor if it existed. Okay, hopefully this is all hand waving high level, but hopefully this example plus like going back and going through the book will ingrain it firmly in your mind. Okay, so this is kind of the bottleneck. If you have a pointer to what you want to delete, it's super fast to do it for cases 1 and 2. For case 3, when you have 2 children, you have to find the predecessor, which is an O of H thing. O of H to do. Because potentially you're at the root, and you got to go down to a leaf that is at the lowest level, down here. So for predecessor, for example, successor is symmetric. You want to go left and then right as far as you can because you want, like here are the smaller things, you want the biggest smaller thing. Yeah? So here's your predecessor. That's how you find it. If you don't have a left child, for example, you want the predecessor of 13, you will start going up because one of your parents is your predecessor. Okay? If the predecessor exists. Like for 1, you'll keep going up. Like there's no predecessor for 1. You'll get to the root and past it even. So if it exists and you don't have a left child for predecessor, the predecessor must be one of your parents if it exists. So you just keep following parent pointers until you find a node with a smaller key. So we know that we can stop immediately once we get to 13. And that's the idea. Usually your book is going to say, okay, the predecessor, if you have to follow parent pointers, you can stop once you find a node that you came up from the right from. Okay, that's the idea. But I like teaching it in terms of just go up until you find a smaller thing. Okay, and yeah, if you go past the root, the predecessor doesn't exist. And in either case, like potentially, like for the one case, you don't have a predecessor. You have to go up the height of the tree. For the predecessor of 5 case, you have to go down the height of the tree. So in the worst case, you got to go the height of the tree. And so if potentially you already have the pointer to the node you want to delete, even still, you might be in case 3 and you have to do O of H work. So no matter what, in the worst case, remove as O of H. Okay. So yeah, just keep all this in mind, and remember, did I have the link anywhere? Probably not. But just remember all this stuff. Like, have this open as you're taking the final. We'll get to these. These are also important. But yeah, just have all this stuff open. The one thing that I don't agree with, we learned about singly linked lists in this class. Did I say that anywhere? Anywhere at all? Dun dun dun. It does not seem to be so. Well, let me put it somewhere. Maybe in Runtime Complexity. Remember, maybe I have it down here. Oh, I have it way down here. Never mind. We'll get to that later. Yeah, let's move on. So recursion is what we're going to go to next. But do keep in mind all this stuff. Singly linked list, I'm going to talk about eventually that deletion is not what it seems. Okay, that is what I want to say there. Let's now move on to recursion quickly, and then we'll head out, and then we'll break for the next lecture. Okay, so first of all, why in the world does recursion work? The idea is, recursion, you have a problem that you're finding in terms of itself, right? Just remember the original definition. And it works because you have a base case and a recursive case. So you have your problem P, and you say, like, you know how to solve a small version of that problem. That's your base case. And then you also know your recursive case, which is saying that, okay, you give me problem P to the n. If only I had this, I know how to get you back one size bigger. I know how to solve a one bigger problem. Okay, you give me P to the n, I can give you P to the n plus 1. And the reason recursion is magic and works is because you will be able to get any number n based on these. Because, say I wanted to solve P of 5, well, how can I get there? I need to eventually use this rule to get up to 5, but I can start here. I can start with P of 0. I know the answer to that. I can use that. I can feed it into the recursive case to get P of 1. I can feed that into the recursive case again to get P of 2. Now feed P of 2, make n equal to 2. I can get P of 3. Then I can get P of 4. And then finally I can get the P of 5 that I wanted. Okay? So that's why recursion works. And let me show you the factorial example just to demonstrate all this stuff. So what it is the base case is, well, first, let's just talk about how to solve factorial recursively, how to understand that it's a recursive problem and come up with a solution for it. So you'll write out, like, okay, what's 5 factorial? It's 5 times 4 times 3 times 2 times 1. And then you'll notice that, okay, I need to find this problem inside of itself. Here it is. Here's 4 factorial. And so then, from there, you can generalize. Generalize to your recursive case. Okay, here's our recursive case. We'll say, okay, not 5 anymore, but n factorial. That must be equal to n times n minus 1 factorial. Okay, that's how we come up with our recursive case. We try an example, and we generalize. And then the base case, that is, okay, you try this on your example now, run this on 5 factorial, and, okay, see where it breaks down. Like, where do you need to stop? That's 5 times 4 factorial, run it again, 4 times 3 factorial, run it again, 3 times 2 factorial. Okay, that all still makes sense. 2 times 1 factorial. Sure, that's fine. That's 1 times 0 factorial. 0 factorial is actually a thing. It makes sense. It's defined to be 1. This, if we were to follow the recursion further, this is 0 times negative 1 factorial. And that is where we start being like, what in the world is that? That doesn't make sense. That doesn't exist. So our base case is 0 factorial. That's where we want to stop and be like, okay, that's just 1. Yeah? 0 factorial is 1, and now we can program this. We can say, that the factorial in the base case, if it's 0, return 1, otherwise return n times the factorial of n minus 1, because that's just a call to fact of n minus 1. And so now fact of 5 will work, and we get 120. And the reason that's all going together and working is because, think of the stack. Like from main, we call fact of 5, which then calls fact of 4, which then calls fact of 3, because it's the recursive case. It needs to multiply by, like, it needs to multiply its 3 by 2 factorial. So we got to calculate fact of 2, which calculates fact of 1, which calculates fact of 0, and that's the final base case. It can stop and return back 1 before it finishes. It's like, okay, my answer is 1. Okay, I was waiting for that. My answer is 1. Okay, I was waiting for that. My answer is 2. My answer is 6. My answer is 6 times, your 6 times my 4, 24. Okay, your answer is my 5 times your 24, which is apparently 120. Back to main who asked for it. Okay, so that is recursion in a nutshell. I have one more example with you of trees, and we will wait until the next lecture for that. And so I'll see you there.